Hello, welcome back to Balanced Three-Phase Circuits. We're working on Wye-Delta problems. This is problem number 3. We're getting there. We're getting a little more complex each time we go along here. And this is not, again, I wouldn't consider it a full-blown problem, but it's definitely more complicated than the last one. So we're given the line-to-line voltage VAB at a balanced three-phase load is 4160 at an angle of 0 degrees. It's telling us the line current IAA is 69.28 at an angle of negative 10 degrees. And for now, just ignore part B. We're just going to focus on part A. Find the per phase impedance for a positive phase sequence. So there's a lot of information here. Again, positive phase sequence, that tells you something. And we're also given some information that we need to label on our diagram. So we're given VAB. Remember, that's a line-to-line voltage in a delta load, because A and B are the terminals of this triangle here, which is exactly the same thing as the line-to-line voltage, VAB. So that's something we're given in this guy. So let's go ahead and label a couple of things. Let's do it right here. So this is going to be, for instance, from here to here, that's going to be VAB, which is exactly the same as it is down here, right? We're given that as a known quantity. And then, let's see here, we're given this guy right here, this current, like this, I, little a, big A, and we're given that problem, or we're given that guy as 69.28, angle negative 10 degrees. This is amps. And what we're asked to find, so we're kind of deciphered the first, almost the first part of the problem, the line-to-line voltage, VAB, okay, that's given to us. We didn't write the number down over there, but we know where it is in the drawing. The line current AA is given by this for the A phase, and then it's asking for the per phase impedance. When it's asking for the per phase impedance, there's nothing else given, nothing else is talked about in this problem. The line impedance, the source impedance, none of that stuff is present. So when they talk about the per phase impedance, the only thing they possibly could be talking about is the impedances of the load, the triangle here, the delta. And if it's balanced, each of these are equal to one another. So when it says per phase, it means this is the impedance for per phase A, or for phase A, impedance for phase B, and impedance for phase C. So the per phase impedance is just Z delta. So we want to find Z delta. So how do we do that? Well, we know from basic circuit analysis that Z delta is just going to be the voltage across that impedance divided by the current going through the impedance. Okay, and we know the voltage across it because that's VAB, right? VAB is given as 4160 at an angle of 0. So we actually have this number. We know this number at the top. We know the voltage across this load, Z delta. But we don't know the current because the current is IAB, and that was not given in the problem statement. We were given IAA. Now you see why it's so important to draw a picture, because if you're just kind of given all these things and you don't really know what a line current and a phase current is and all that stuff, and you don't draw anything, you're going to be tempted to use this current and stick it in here and get the wrong answer. But this is not the current flowing through this load. This is the current coming in from the line direction. So what you need to do is convert, because we know the line current. We can then find the phase current by using our square root of 3 rule. That will give us this current, and then we'll have both pieces of information to find the load impedance Z delta. So that's going to be our strategy. So what we're going to do over here is we're going to say that IAA is equal to the square root of 3 times IAB at a phase shift of either negative or positive 30 degrees. Then we go back to our problem statement, and it says, what does this say here? Balanced three-phase load, line current